everyone, and welcome back to The Explainer. I am absolutely thrilled to be here with you today. Before we dive into the fun stuff, I want to quickly mention that this explainer is brought to you by Forge College. Now, if you joined us for our previous lesson, Core Principles of Borsh, you already know the low-level encoding basics. Today, we're taking those raw mechanics and applying them to the real world in our new topic, mapping data structures to Borsh. To make this super intuitive, I actually want you to imagine Borsh as an ultra-strict, no-nonsense baggage handler at the airport. Listen, this handler doesn't care if your suitcase is designer or covered in cute stickers. They only care about packing the cargo hold exactly according to the manifest, byte by byte, with absolutely zero wasted space. So let's see how our data actually gets packed. All right, here is our flight plan for today. First, we'll look at translating Rust to bytes. Second, the wireform rules. Third, real-world account layouts. Fourth, we'll cover some smart mental models. And finally, number 5, migration and upgrades. Let's get right into it. Section 1. Translating Rust to bytes. Okay, here is your golden rule. Seriously, write this down. Declaration order equals byte order. Remember our strict baggage handler? You can't just shove a pair of socks anywhere you want to make them fit. Every single piece of data goes exactly where the struct manifest says it goes, right down to the byte. In Borsh, if you declare field A and then field B, field A's bytes are written first, immediately followed by field B. There is literally no implicit padding inserted between values and absolutely no secret metadata tags hiding in the background. It is wonderfully, ruthlessly efficient. Moving right along to Section 2, the wireform rules. So how does our strict baggage handler actually wrap up different types of items? Think of this like an engineering cheat sheet for our data types. Fixed-sized primitives, like a U8, a U64, or a Boolean, they have a completely predictable footprint. A U64 is always exactly 8 little-endian bytes, period. But things get interesting with dynamic types. Strings and vectors are flexible, right? So Borsh packs them by writing a U32 length prefix first, followed by the actual payload. Options get a simple 1-byte presence tag, basically a simple yes or no flag indicating if the data's even there. And enums get a U32 variant index followed by the payload for that specific variant. Mechanistically, your job as a Solana developer is to constantly contrast the predictable footprint of those fixed items against the dynamic sizing of the variable ones. Let's jump into Section 3, real-world account layouts. Let's move from abstract theory to a concrete real-world layout. Imagine a Solana program that stores a user profile. We have 5 fields declared in this exact step-by-step order. Version as a U8, is active as a Boolean, balance as a U64, username as a string, and an avatar as an optional vector of bytes. Now think about how our baggage handler views this sequence. They don't see a user at all. They just see a 1-byte item, another 1-byte item, an 8-byte item, a dynamic length string, and finally a maybe-present dynamic length image payload. And this brilliantly illustrates how those exact fields look on the wire when we actually populate them with real data. Let's say our user is named Alice, she has a balance of 1,000, and she didn't upload an avatar. The first byte is 0x01 for the version. The second is 0x01 because she's active. The next 8 bytes, that's the number 1,000 represented in little-endian hex. Then, because the name Alice is exactly 5 letters long, we get a U32 length prefix of 5, followed by the actual hex codes for the letters A, L, I, C, E. Finally, a single 0x0 byte for the avatar, which just means none. It is a pure deterministic translation. Now, the crucial point I want you to take away is right here, the number 10. Notice that the first 3 fields, the version, the active flag, and the balance, take exactly 10 bytes every single time, no matter what user profile we are looking at. This predictability is an absolute lifesaver. You can always blind read byte 0 to get the version, or bytes 2 through 9 to check a balance, without having to deserialize the entire account. But here's where we run into a bit of trouble. The unpredictable tail. Because the username length varies from user to user, the exact byte offset where the avatar starts is completely unpredictable until runtime. It depends entirely on how many characters the username has. On Solana, this has massive operational consequences. Account data sizes are fixed at allocation. If Alice decides to change her username to Alice_in_Wonderland, the total size of the struct expands. If you didn't leave empty space at the end of the account, this dynamic growth triggers expensive account reallocation and demands additional rent payments on the network. Ouch. So how do we avoid that? That brings us to Section 4, smart mental models. To avoid those costly rent surprises and reallocation headaches, we really need to equip ourselves with some architectural best practices. The first, and honestly, arguably the most important model, is fixed head versus flexible tail. You should consciously split your structs into two zones. Group all your predictable, fixed-size data, like numbers and booleans, at the very front. This is your fixed head. It guarantees stable byte offsets, which makes in-place updates trivial and fast. Then throw all your variable length items, like strings and options, to the back. This becomes your flexible tail, effectively isolating all that unpredictability to the end of your data block.
Our second mental model is pointer by reference. Let's go back to our baggage handler for a second. If you have an aggressively oversized item, like, I don't know, a giant pop-up tent, you don't try to stuff it into your carry-on luggage, right? You check it. On Solana, if data might grow unbounded, like a giant high-res user avatar image, don't stuff it into the main account. Instead, store a compact program-derived address, or PDA, reference in your main account, and put the massive unbounded blob in a secondary, completely separate account. It keeps your primary account lean, mean, and cheap.
And finally, Section 5, migration and upgrades. Because let's face it, eventually you are going to need to change your data blueprint after it's already live on-chain. When you need to upgrade, you can't just randomly insert new fields into the middle of your struct. Doing so shifts all the subsequent bytes and causes older deserializers to completely panic when reading the new layout.
No way.
Instead, use one of these 3 compatible migration approaches. First, version tags, checking a version byte at the very start to route to the correct layout. Second, enum-based variants, wrapping the entire account in an enum, letting the numeric discriminant handle the versioning. Or third, the append-only extension, safely adding brand new fields exclusively to the very end of the struct so older clients simply stop reading when they run out of the fields they recognize. You can also use a clever technique called capacity budgeting. This just means pre-allocating a vector or using a fixed byte array to reserve space for variable length fields you expect to update frequently. Reserving this space acts as a vital buffer against constant account reallocation. However, as an engineer, you have to weigh this benefit against the cost of over-provisioning rent for space that might just sit empty. It's definitely a delicate balancing act. Ultimately, designing Borsh layouts is a practice of translating deterministic encoding rules into predictable, maintainable data shapes. Mastering these layout rules, really understanding exactly how the baggage handler packs the cargo hold, doesn't just make your code cleaner. It literally makes you a vastly better, more cost-efficient Solana developer. So we know how to pack our data perfectly, but how do we wire these serialized accounts into Solana program entry points securely without opening ourselves up to malicious payloads? Well, that is exactly what we will tackle in our next lesson, integration considerations for Borsh. I highly encourage you to visit forge.college to check out that lesson, explore more about this subject, and dive into a wealth of other Web3 related topics. Thank you so much for hanging out with me on this explainer today, and happy coding!